So let's say a few words about genetic code because it will become important when we will talk about mutations eventually. So everybody knows there's a genetic code. It's universal, turns out. We often, I think, underappreciate it. Now, what is the purpose? The purpose is to make a code that can be used by ribosomes to read, and we need to make names for 21 amino acids, first of all, right? It's 21 amino acids. Therefore, we need to make words out of 4 letters. A, G, C, U, if it's RNA, or G, C, T, if it's DNA, it doesn't really matter. Good? So, obviously we can't use single word letters, because there's going to be 4. And we can't use double word letters, because there's going to be 16. So at the end of the day, each amino acid has a 3-letter code, words, okay? So this is going to be a codon, and I remember only 2 of them. I never memorized any of that crap, okay? So I accidentally remember that AUG encodes for methionine, it's a start codon, yes. And CCC encodes for amino acid proline. Okay, that's it. Other, whatever, I don't remember. Okay? Please do not memorize any of that crap. Okay? It's BS to memorize the codons. I use it to illustrate a concept. We good so far? So, first thing, we have 21 amino acids. Plus we have 3 stop codons, I know that. But at the end of the day, we have 64 3-letter words. So we have more words than objects to name. This is why genetic code is degenerate or redundant. Which means each and every one not each, but some amino acids can have more than 1 codon. Does that make sense? So, if I describe an elephant, I can say that elephant is big, large, huge, or enormous. All those 4 words mean the same. So, if I describe amino acid valine, I can use, I think it's valine, like 4 different codons, or 6 codons, like insane number. Does that make sense? What's important to understand? An amino acid can be described, quote unquote, by more than 1 codon. But each individual codon corresponds to a single amino acid. Does that make sense? So if you take a random one, it will be, for asparagine. Not for anything else, just for asparagine. For whatever matches. So far we good? Okay. Now, how do your ribosomes know which amino acid should be inserted here? tRNAs. Typical tRNA molecule, transport RNA molecule, has poetically named cloverleaf shape, which it doesn't. It just has a weird shape, okay? Which can be exemplified of sorts, schematically, as a cross. Okay? At this end, you have amino acid. And at this end, you have a recognition structure, which is called anti-codon. So this AUG is a codon. And what's going to be the complementary sequence for AUG? U, A, and C. Does that make sense? And this is anti-codon. The recognition is, so I myself, when I routinely think about translation, I think of it as a highly organized process where, like this this transport RNA that carries methionine just snaps into the first place perfectly, like two perfectly matching Lego pieces. Which is not. Like, okay, Lego may be not a bad analogy. So when you assemble Lego, you have instructions, right? And like, just look, okay, I need to take this and snap it here. Now imagine you have, I don't know, 6-month-old who is just absolutely randomly just puts them together. If they match, if they can be clicked, they will. But if they won't, he will throw that detail out and grab another one. Does that make sense? This is what happens at the ribosomes. If anti-codon does not match codon, this tRNA goes away, another one comes in. There are no little tiny Oompa Loompas within the ribosome that just pull the tRNAs out of the cytoplasm. Does that make sense to you? So that's tRNA. Okay. Yeah, that was an explanation. So let's get back to translation. What happens during translation? It's going to be terrible. So first we need to assemble the whole complex. So we're going to start with mRNA. Obviously, we can't do translation without mRNA. And the first ribosomal component that will sit on mRNA will be small subunit. It will be small subunit of the ribosome, right? How does the small subunit know where to sit? So the recognition structures so-called Shine-Dalgarno sequence in prokaryotes, okay? It's a special sequence that is on the RNA. So ribosome recognizes the sequence and says, I'm slapping myself here. Does that make sense? And on eukaryotic RNA, there is so-called 5' cap. Now, I have a very serious suspicion that you are looking at it and maybe thinking, what is the relevance of this 5' cap crap? Like, why? How is it relevant to microbiology? Well, let me put this in perspective. If you remove 5' cap, ribosomes cannot recognize mRNA. Does that make sense? And there will be no translation. Guess what? Viruses it's called cap snatching. They can take the cap, 5' cap, off the cellular RNA, making all of them inaccessible for the cellular ribosomes. So viruses now can use ribosomes all for themselves. Does that make sense? It's really a phenomenon, an interesting phenomenon. So small subunit binds, and then the whole picture is completed by the first tRNA, which binds to the start codon, and the large subunit. Okay, and your I'm actually gonna make tRNA much smaller. You will see why. So this tiny little tRNA here with methionine. Okay. And your initiation complex is good to go. Okay. Now what happens next? Turns out, in the large subunit, you have three so-called sites. This one here sits in the P site. The site here, we're going to do it slightly different this time. The site here is A site. And the site here is E site, which gives us a perfect word for an animal. ape. Okay? I'm going to show just one step of transcription. So let's say your second amino acid here is proline. Okay? So the codon here is CCC. Next tRNA comes in, carries proline. How does it know that it should be there? How does it snap itself there? Because it carries this entire codon GGG. Okay, we're good so far? Good. Moving on. Next, the enzymes within the ribosome transfer proline onto methionine. No, sorry, the other way around. I'm sorry, I apologize for it. The other way around. It's kind of important. Okay? Now look what happens next. Here I will appeal to your imagination. This whole ribosome shifts to the left, one place. So this tRNA, which is now empty, ends up in the E side. Everybody sees that? Okay? This tRNA, which now carries dipeptide, ends up in the P side, and A side becomes empty again. Are we clear? So A side becomes empty for the next step, for the next incoming tRNA. We can show it, no worries. Okay, so far we're good? Yeah, couple more things about the whole process. It's pretty fast, and it takes a lot of energy. As far as I remember, introduction of a single amino acid requires like two, yeah, I think it is two, what's the word? 2 ATPs. So if you need to make one protein, 100 amino acids, like 200 ATP molecules, that's a lot of energy. So far we good? Any questions here? Okay.